Hello, this is my equation for the vibrational frequency of a pyramid, a three-sided equilateral tetrahedron. So that's it. That's the equation. It's a simplified engineering equation. The velocity, this is your frequency. It equals velocity divided by 3 times a. It's really fairly simple when you boil it down to that. The velocity is going to be the speed of sound in whatever material you're using. And you can get that from charts online. Okay. In this case, these are the tested values. I tested this as shown in the video with sound analysis. And so that's the actual frequency of these objects when struck. So when you strike them, you have to throw them in the air. You can't just hold them because it'll change the vibration. So to throw it in the air and strike it, and there's a sweet spot about a quarter of the way down. If you hit it just right, it'll vibrate. And you need to hit it with something hard, but it can't be like another steel object or something, because then it will vibrate and interfere with your results. So you have to throw it in the air, and you have to strike it with something like a rock or hard plastic or something to get it to vibrate long enough to where you can hear it. And I slowed the footage down by a factor of 1/8. I slowed it down by 1/8 so that you could get it into the human hearing range. So 3 times A is just this distance here in meters, velocity in meters per second, and 3, it turns out it's very simple. It's just 1, 2, 3. That's the magic distance that allows you to determine the vibrational frequency. Now, this equation was based on other equations, right? Hooke's law is the vibrational frequency equation. Poisson's ratio is relating to the material science. Young's modulus is relating to the material science. But all of these are previously existing engineering equations. You can get your speed of sound that way. And of course, it changes with temperature and the material and the casting technique, etc., etc. But this equation, this is new. This is my equation. You won't be able to find that if you go to ChatGPT and say, hey, how do I figure out the vibrational frequency of a three-sided pyramid? It's going to give you a bunch of bullcrap answers. But this is the actual tested method, and it comes out pretty close. When you plug those numbers in, you come up with, for the aluminum, this range, and when tested, that's the range we're getting. For the copper, you get this range, and when I tested it, that's the range I got. So, I want to give credit to the SPECTROID app, WavePad, and CH, I believe it is. And then, of course, ChatGPT. But you got to keep ChatGPT between the rails. I want you to enjoy the rest of this video test footage, and we'll talk a little more in a minute.
Doing it right, everybody will be dancing and we're feeling it right. Everybody will be dancing and we're doing it right. Everybody will be dancing and we're feeling it right. Everybody will be dancing to it, doing it right. Everybody will be dancing and we're feeling it right. Everybody will be dancing and we're doing it right. Everybody will be dancing and we're feeling it right. Everybody will be dancing.
Now that we've seen some test footage, let's discuss the possible applications of this equation. If you compare the amount of open space in a solid metallic object, such as these, with the distance between planets in a solar system, proportionally speaking, there's more distance between atomic nuclei in solid materials than there is between planets in the solar system. For example, if we compare the distance of the Earth to Mars in terms of Earth diameters, it can be as close as 4,300 Earth diameters away. If you look at the distance between atomic nuclei in materials such as magnesium, the distance between atomic nuclei in terms of nucleus diameter is about 160,000 nuclei diameters. So proportionally, there can be more empty space in solid materials than there is empty space in a solar system. Now that empty space is filled with electrons, but electrons do not behave necessarily as particles. The reason I'm using magnesium as an example is because magnesium has an atomic geometric arrangement known as HCP, hexagonal close packed, which when carefully viewed you can see is actually the same thing as a three-dimensional grid of triangular pyramids. So the spacing between atomic nuclei is the same as the spacing of the points on a three-dimensional pyramid. When we take this equation that I have and use it in the case of something like magnesium at a very small scale, you can put in the velocities associated with electron behavior, and you will get some interesting results. The slowest electron vibration is called drift velocity, and with that you will get a vibrational frequency in the kilohertz range, which is a very low radio frequency range. So that might be useful for testing in radio frequencies using magnesium as a material for either transmission or absorption of radio frequencies, if you get the frequency correct. Another interesting thing that ChatGPT helped me with is to substitute in here the velocities associated with electrons that are close to what they call a Fermi velocity. So when you insert these different electron velocities into this equation and use A not as a distance measured manually by your hands, but of course A would be the distance between atomic nuclei in magnesium, you find these results that have an interesting correlation here. And that correlation is that the frequency that I get is remarkably close to the frequency associated with magnesium's Fermi energy. I'm getting the same results with my equation that a different equation with different inputs predicts the frequency would be. So I think this is an interesting equation. I think it has some use, and you're not going to find it anywhere else on the internet but here, as far as I know. Scientists have tested spheres and other shapes, but no one's ever really in-depth tested this shape. And ChatGPT can make up stories about it, but without actual testing, you really don't know until you actually test it. And this is, again, ballpark. Maybe it's 3.1, maybe it's pi, but from my testing, it's about 3 times this distance. That's your magic number there. And so what I would like someone else to do is to cast this bad boy out of magnesium. Now, I can't cast it out of magnesium because, well, it'll burn. Magnesium is flammable. But with the right kind of furnace, an electric arc, an induction type furnace with filled with an inert gas like nitrogen or argon, you can melt magnesium and cast one of these out of magnesium. And that might be another interesting test, is to correlate the macroscopic vibrations with the microscopic electrical vibrations and see what you get. Thanks for watching. Hope you enjoyed.